Good afternoon, everyone. Today I'm going to present the work DPS, System Algorithm Co-Design for Asynchronous and Heterogeneous Cross-Cluster LLM Training at Scale. This is a joint work between National University of Defense Technology, Shanghai AI Lab, and the Nanyang Technological University. Before I start, just as a brief disclaimer, I'm not an author of this work, nor did I participate in it. I'm not affiliated with the institutions. I'm the volunteer presenter on behalf of all the authors who cannot attend today. All credit and any follow-up questions should go directly to the authors. Let's start with the broader trend of LLM training. As Qiaoling laws continue to hold, the amount of training compute required for large language model is growing exponentially. However, hardware performance is not improving at the same pace, which creates a widening gap between compute demand and supply. At the same time, the scale of training clusters is rapidly increasing. For example, Llama 3.1, it uses around 16,384 collaborators, while Grok 2 uses about 20,000, and Llama 4 scales up to 33,000 accelerators. So today, large-scale LLM training has already entered the tens of thousands of devices regime. However, there is a key mismatch between training demand and real-world infrastructure. In practice, about 85% of clusters have fewer than 10,000 NPUs, and only a small fraction can reach the scale required by modern LLM training. This means a single cluster is often insufficient to support large-scale training. Therefore, aggregating multiple clusters together becomes a natural and necessary solution. Beyond necessity, cross-cluster training is also more practical. Compared to building a single monolithic cluster, consolidating existing smaller clusters offers several advantages. Lower cost, since it reduces the need of expensive hierarchic switches and networking infrastructure. Easier deployment, as smaller clusters better fit power, cooling, and space constraints. Better resource matching, because most workloads do not actually require extremely large clusters. And higher operational efficiency, since ultra-large clusters are often harder to utilize effectively. Let's look at the current standard approach. In cross-cluster settings, the inter-cluster network is orders of magnitude slower than intra-cluster communication. To address this, existing systems adopt a two-stage optimization strategy. Each cluster performs multiple local training steps using an inner optimizer. Then, a global outer optimizer synchronizes models across clusters at a lower frequency. This reduces communication overhead, but it also introduces staleness and coordination challenges, especially under heterogeneity. One representative system is dLocal, which adopts a decentralized architecture. In this design, each cluster maintains a replica of the outer optimizer, and these replicas are synchronized using collective communication across clusters. While this approach improves scalability to some extent, it still relies on relatively rigid synchronization patterns, which limits its ability to handle asynchrony and heterogeneous cluster performance. Now, let's look at the key challenges in cross-cluster training. The first challenge is inefficient cross-cluster communication under heterogeneity. Existing two-stage methods typically adopt a decentralized architecture, where each cluster maintains a replica of the outer optimizer and synchronizes via collective communication. However, this design suffers from a critical issue. Communication becomes bottlenecked by the slowest link. In practice, inter-cluster bandwidth varies significantly, and decentralized communication is highly sensitive to this heterogeneity. As a result, overall performance is often dragged down by clusters with poor network conditions. The second challenge is unstable convergence under asynchronous training. Because clusters are heterogeneous in compute performance, asynchronous training is necessary to avoid stragglers. However, when we directly apply a synchronous update to existing methods, such as async delocal, we observe that training may fail to converge or become highly unstable. This is because stale or low-quality updates can easily accumulate, especially when cluster speeds differ significantly. The third challenge is dynamic and unreliable clusters. In real-world production environments, cluster performance fluctuates. Failures are frequent, and resource availability changes over time. As shown in their 33-day production trace across 9 clusters, failure rates and resource variability differ significantly across clusters. In decentralized systems, handling these failures requires expensive coordination across all participants. So overall, they are facing 3 challenges. Insufficient cross-cluster communication, unstable asynchronous coverage, and dynamic and unreliable clusters. Next, the question becomes, how can these challenges be addressed? The key observation is that a centralized parameter server architecture offers strong opportunities. Compared to decentralized designs, a centralized PS provides better bandwidth utilization by leveraging high bandwidth links more effectively. Global optimizer history, enabling better control over updates, and failure isolation, since cluster failures can be handled locally at the PS. These properties directly align with the challenge identified. Based on this observation, 3 key requirements are derived from cross-cluster training. First, scalable efficiency. Efficient parameter exchange is needed over heterogeneous networks. Second, stable convergence. Stale or abnormal updates must be detected, and asynchronous training must be stabilized. Third, resilience. The system should isolate failures and support dynamic cluster join and leave. Based on these requirements, they produce DPS. At a high level, DPS adopts a leader-follower parameter server architecture. Multiple follower PSs are distributed to share the outer optimizer state. A leader PS is responsible for global scheduling and coordination. In addition, they design a dual workflow mechanism to reduce communication contention across clusters. Let's first talk about how they achieve scalable communication. In DPS, follower PSs and training clusters communicate in a many-to-many pattern instead of rigid all-to-all synchronization. The scheduling design has 2 key goals: fully utilize cross-cluster bandwidth and follow a flexible communication across clusters. To achieve this, they use a greedy mapping strategy, which enables high concurrency parameter transfers and independently generated schedulers for each cluster. This makes the system both scalable and adaptive to heterogeneity. In addition, it further improves efficiency through operation overlapping. Follower PSs are responsible for outer optimization and the pipeline 3 steps of operations: communication, computation, and storage. By overlapping these stages, they significantly reduce idle time and improve overall throughput. Next, to address unstable asynchronous covariance, they propose pseudo-gradient correction. The key idea is simple. Use historical information to detect and filter low-quality updates. Specifically, they compute the norm of each cluster's pseudo-gradient, evaluate quality based on both norm and updated history, and filter out abnormal or low-quality gradients. Finally, they aggregate only the high-quality updates by the amount of training data consumed. With this mechanism, DPS achieves stable convergence even under strong heterogeneity. In fact, the results show that convergence is comparable to synchronous training, and downstream task performance is nearly identical. Finally, they address resilience. In real training, resources are highly dynamic, with frequent scale-in and scale-out events. They design a heartbeat-based elasticity mechanism. The leader PS continuously monitors cluster and forward PSs. Failed clusters are removed from optimization while others continue, and failed follower PSs are automatically restarted. This allows the system to gracefully handle failures without global interruption. Now, let's move to evaluation. DPS is evaluated in both real and emulated environments. 16 real clusters, with up to 8.18 times the performance variation. 16 emulated clusters, with controlled delays. They also simulate heterogeneous networks, where one cluster has reduced bandwidth. The test was on Llama 3.2 with 1 billion parameters and Qwen 3 with 14 billion parameters, and compare against DP, dilocal, and asynchronous dilocal. In end-to-end performance, DPS achieves 1.27 times to 4.67 times speedup over convergent dilocal, and up to 1.6 times improvement over async dilocal. Importantly, DPS maintains comparable model quality to synchronous methods. They also evaluate scalability. And they increase the number of clusters, first in homogeneous and then in heterogeneous settings. DPS achieves more than 98% of ideal scaling efficiency. Finally, they deploy DPS in a real production training. They train a 100 billion parameter llama-based model using up to 9 heterogeneous clusters, totaling over 10,000 devices with 16 follower PSs. The training runs for 33 days and processes 2.3 trillion tokens. The results show that a stable training loss, stable system performance, and expected model quality. To conclude, the authors study cross-cluster LLM training under real-world heterogeneity and identify 3 key challenges: communication inefficiency, unstable asynchronous convergence, and poor fault tolerance. The key idea is to use a centralized parameter server architecture combined with system algorithm co-design. They built DPS with a scalable leader-follower PS architecture, a pseudo-gradient correction for stability, and a heartbeat-based fault tolerance. The results shows that DPS improves training throughput while preserving model quality. DPS scales to more than 10,000 devices and trains a 100 billion parameter llama-based model for 33 days. Thanks for your attention. If you have any questions, please feel free to contact the authors directly by email.